Good morning, good afternoon, or good evening, wherever you are. Welcome to Percona Live. And today, our presentation topic is the power use of indexes in Postgres. And myself, Jobin, and I have Sergey along with me for this presentation. And we'll be covering different types of major indexes available in Postgres and its uses. It gives a user perspective of indexes. And yeah, myself, Jobin. I am a Postgres escalation specialist in Percona. It is the third year in Percona now. I have been into Postgres for quite a bit of time. And I'm handing over to Sergey for introduction.
Hello, everyone. My name is Sergey Kuzmichev, and I am a senior support engineer here in Percona. Before joining Percona, 1.5 years ago, I worked as a DevOps engineer, and before that, as an Oracle DBA. And while working as a DevOps engineer, I got my hands on PostgreSQL, and I haven't stopped ever since. So, Jobin?
Yeah. Oops. Yeah.
Okay, so in this presentation, we are going to be talking about PostgreSQL index types, both included and the single external index type, which is RAM. I will talk about two boring indexes, the B-tree and hash index, and Jobin will talk about the interesting index types. And so I will start with the, with the B-tree index. Okay, so the bitrate index is the most common index type. It is the default, which is used when you run create index. And I could bet that it's probably used in most PostgreSQL installations, actually used by catalog, tables, and views. So it is the only index type supporting the return of ordered results. It's the only index type that can support uniqueness constraints. It does support index-only scans, and it supports range scans. The B-tree index is a tree. Each leaf stores a key, and it also stores a reference to a tuple. The tree has predictable search performance. We expect that every key lookup will take the same amount of time. And a bit of trivia, the PostgreSQL actually uses not the regular B-tree, but the blink tree. Well, when do you want to use B-tree index? Well, the important thing is that the B-tree index is general purpose, so you can probably use it whenever, but you should absolutely use it when you need a unique constraint, when you can cover your queries and serve index-only lookups, when you need sorted access patterns, and when your data has high cardinality. B-tree index will struggle with low cardinality data. It will also struggle with really large volumes of data, and there are difficulties with lookups on subsets of columns. So let's talk about sort operations. Every range lookup that is served via B-tree index is sorted. Optimizer can use that. It can pick either to read index for sorted results or read heap and then do the sorting. B-tree index's sort order is defined upon creation, and it can be B-tree indexes can be accessed forward and backwards, as we will show. Unfortunately, not every B-tree index is suitable for every sort access operation, and you should really try to avoid creating an index for every query. Otherwise, you will just have too many indexes and a huge overhead. Okay, so this is a basic example. We are selecting from a table, and we are ordering ascending order, and we are using just an index scan. And then we are doing a select, doing the descending order. And since the index was built in ascending order, PostgreSQL can scan that index backwards to actually satisfy the descending ordering. Slightly more complex example with two columns in the index. The index is built using both columns in ascending order, and we can see that if we order by both columns in ascending order, an index scan is used, index-only scan, in fact. If we do both columns in descending order, a backward index-only scan is used. However, if we select and order each individual column is in its own order, PostgreSQL cannot use the index to satisfy the ordering. It will, in fact, use the index-only scan, but it will only use it for sorting the results of the first column, and then it will have to actually run another sort on top of that to sort the result set. So let's move forward. The bitrate index has a size problem. Since we store a key and there are no sparse bit trees, you actually have to store every key that you index. The wider the keys, or the more columns in an index, the larger is going to be the footprint of the index. There are, however, solutions to this problem. There are partial indexes, and the partial index is an ability to create an index that only covers some key values. And there is also an index tuple deduplication that came in as a feature in PostgreSQL 13. Let's start with partial bit-tree indexes. So it is possible to create a bit-tree index on a subset of key space. And this allows you to minimize waste. For instance, you have a column that has low cardinality, and you are only really interested in a single value of a key. Like there is a flag which can be true or false, but you only need to filter by flag equals true. Or you can have a column key distribution which is skewed. There are a few rows that have multiple values, and there are a lot of rows that have same values or just the same value. Building partial bit-tree indexes wherever possible really significantly decreases the index size and takes down operating costs, and it can improve query performance quite a bit. Unfortunately, not every partial index is suitable for every query, so they are not really universal. You have to specify filters that can be guaranteed to use the partial index, and I will show that in a bit. So, a simple example. We have a table that has a lot of rows and it's growing. One of the columns value is 0 when the row becomes inactive. There are very few active rows and a lot of inactive rows. So we can see here that when this column is 0, there are almost 1 million rows there, and just under 100,000 rows have this column non-zero. So it is highly likely that we will be more interested in active rows here, and indexes can help with that. Both the regular bit-tree index and the partial index. So let's try to see how it works. So we create two indexes. One is just using the bit-tree on a column, and the other one is using the bit-tree on a column, but specifies a where clause. And the where clause tells the create index operation which values it has to actually index. And immediately we can see that the regular index is much larger than the partial index. Even with the improvements that came along in PostgreSQL 13, even with the deduplication of the values, the index is still a few times larger than the partial index. And before PostgreSQL 13 or with the deduplication disabled, the index is almost 20 times larger. Unfortunately, partial indexes only work when queries tell explicitly that they don't need this skipped so-called data. So if we query our column, our table, and tell that our column, we don't need results based on the column values that are non-zero, we only need results that are non-zero, Optimizer can pick our partial index. or if we just specifically ask for a specific value, which is non-zero. However, like you can see in the last example on this page, if we run a query where optimizer cannot really guarantee that the filter will not return a zero, the partial index cannot be used. This is especially important when you are doing joins, because you might really, because optimizer might not be able to predict whether an indexed value is going to be used, and so the partial index may not be used actually. The other solution to the problem is the bitrate tuple deduplication. The problem is, more often than not, the key values are not unique, and often key value distribution is skewed. There are many occurrences of a few values and a few occurrences of many values. So the partial indexes, as I explained, are not universal. No, they don't fit every query, and it's not always possible to predict which columns you should pick, which values you should select. So the solution is we may actually not store full information on the duplicate values in a regular B-tree index. And this is a feature in PostgreSQL 13 called deduplication. So this is a little quote from the documentation of PostgreSQL. And the duplicate is a leaf page tuple where all indexed columns have values that match corresponding column values from at least one other leaf page tuple in the same index. This is a lazy process. You can read documentation about the deduplications. We won't go into deep technical details, but a few words here. The process of deduplication is lazy. It will happen eventually, but you can kind of force the deduplication using create index and reindex commands. Deduplication gives some performance penalty on writes, and especially if you have an index where you predict that there will be no similar values, like this is a unique index, you can actually disable the deduplication on the index level as a storage parameter. So there are some limitations in the tuple deduplication. It cannot be used with character types with non-deterministic collations. Think case-insensitive collations or collations that mix together different accent marks. Because otherwise, if we would use the deduplication with non-deterministic collations, we could lose data from similar values. We cannot use it with numeric types, with JSON bit type, it is numeric underneath. We cannot use it with float types, container types, and we also cannot use the include option of the indexes. So there's an example that I already shown you with the same column where a lot of values have 0 and only a few rows have non-zero value of some column. And we create two indexes. One index is using the deduplication and the other index does not. And the deduplicated index is just under 8 megabytes in size, whereas the not deduplicated index is 21 megabytes in size. This is a huge win, and it comes pretty much for free. Of course, there is some overhead, but yeah, not a lot. There are also some more examples here. So we are using the some database where there are cast members and they all have different roles. And it is reasonable to expect that there is going to be fewer different roles than members, than crews of the cast. And so we have the index that is 14 megabytes in size versus 25 megabytes in size. Again, a pretty good win. Okay, and now we are going to talk about the bitrate include option. We actually covered it in a bit before, mentioned it. So what is the include option? The include option allows you to improve index-only scanning but minimize the drawbacks. It allows you to improve covering of your queries with indexes. This feature allows you to store column values in leaf node tuples, but not store their values in upper-level navigation entries. What this means is you can add additional columns to the index, but those columns cannot be used for search in the index, but their values can be returned. An example is query often needs first and last name by person ID. Regular composite index is going to be wasteful. While ID is unique, first and last names are redundant, and if you're really querying only by person ID, you don't need an index that would include the first and last names. You will never use it for search. However, you are frequently need the first and last name, even though you are querying by person ID. And what is also neat about include option is that it can enforce unique constraint on the person ID, but not enforce the uniqueness on the first name and last name simultaneously. So what you can do is you can create an index, and you can see that this is a regular B3 index, but it has the include parameter. And we include passenger name into our index that is based on the passenger ID. And now when we are selecting a name from our table by the ID, we use index-only scan. So this is a huge benefit. Yeah. But you cannot use the index backwards. So you cannot get any information from this index by passenger name. So it really only uses passenger ID for search. So one more neat feature of indexes in Postgres, and it's not limited to B-trees, but we're covering it here because it's pretty basic and universal. So this is an ability to create expression indexes, indexes on expressions. The problem we are trying to solve here is our query uses some expression. For instance, the really basic example is a query that does a search, a comparison with lower function of the name. And you can see immediately that the regular B3 index is not used. The sequential scan kicks in. However, if we actually build an index on the lower expression, we can actually use that index. So we can see that the bitmap index scan is used, even though we are using a lower name in our where clause. We can also use expression indexes to avoid using generated columns, to minimize this the size of the table, to improve table scans. So for example, here we can assume that sometimes we need to search by a hashed value, and we could store a hashed value column in our table or create a generated column, but instead we can just create an expression index on the hash function and query it like this. So this is an example. Okay, so that is pretty much it for the B3 indexes, and I move forward to hash indexes. So hash indexes are quite interesting. They're probably the most basic and simple indexes that PostgreSQL has to offer, and they really have a bad reputation. Because before PostgreSQL 10, PostgreSQL itself recommended to never use them. Like when you created this index, you got a nasty warning about the fact that hash indexes are not vol-logged, they are not replicated, they are not persisted upon restart, so they were not really good. However, they are quite simple, and there are use cases for them still. So the hash indexes are basically just hash tables. They store buckets of TIDs and hashed key values. There are very few bucket values, and the buckets store pairs of the TID to key value hash. The hash index can only serve lookups for equality, so only equality operations can be satisfied with the hash index. No ranges, no larger, no smaller, only just equality. Okay. So this is a simple representation of a hash function of a key and buckets from the Wikipedia. The hash function selects bucket for each key, and we store hashed value of a key. Everything is automated. The function is predetermined. The bucket management is automatic. You don't need to worry about this, but it's just some internals of the index. Okay. The hash index storage is pretty simple. It's organized with 4 page types. There is a single meta page storing some internal information. The bucket pages store the pairs that I mentioned, the TID key-value hash pairs. There are also overflow pages that appear when you insert a lot of information and bucket pages overflow. And the bitmap pages store information about the overflow pages that are vacant and can be reused. The hash indexes are page-based and they don't grow linearly. The new bucket pages are added as you insert data, and hash index tries to predict how much pages you will need. The vacuum of hash indexes doesn't return space. It only frees up pages for future use, like it marks overflow pages free and populates the bitmap pages with the correct information. And if you need to reclaim space, you have to re-index or vacuum full. So again, they store hashed key value. A hashed key value has uniform size regardless of key length. Depending on key value, lengths can minimize storage overhead or increase storage overhead. This is actually going to be good for longer key values. Okay, a bit more. We can only serve lookups for equality, as I mentioned. And this severely limits their use, but it can still be useful. You could have a lot of unique or almost unique keys. And remember, we cannot use hash indexes to base a unique constraint upon it, right? So that can only be done with the bitrate index. The hash indexes will also be useful for longer key values because the bitrate index stores the specific key value, where the hash index only stores the result of the hash function. Okay, some examples. So if we create a hash index on a key value with a relatively small key, right? So we see that the hash index is actually larger in volume than the bitrate index. However, as soon as we switch to pretty long keys, our hash index is going to outrun the bitrate index in its compactness. The longer the values, the larger is going to be the difference between the hash and the bitrate index. So this is a database of malicious URLs, and this is an index on the specific URL, which is, I created a hash index and the bitrate index, and you can see that the hash index is pretty smaller than the bitrate index. And by default, hash indexes have slightly lower fill factor than the bitrate index, 75 compared to 90. So if we equal them in the fill factor, the hash index is going to be even more compact. But beware that increasing fill factor of the hash index will increase slightly the write overhead. Okay, so hash indexes in queries. As I mentioned, here we are using a hash index based on the URL. And this is a great example because you really rarely do like a URL larger than or smaller than or anything really than equal, right? So the larger than for a string, and specifically for a URL, doesn't really make any sense in the real world. So you are probably going to use equality here. And the URL as a key value has pretty big lengths. And so we can see that hash index is used, and we can use hash index for the ID lookups. Of course, we can build hash index on pretty much any column. And we can also see that we cannot really use the hash index on the anything but equality operations. So as soon as you do lesser, you are getting the sequential scan. Okay, so a short recap. The hash indexes are good for long key values because they will have predictable storage footprint. They're good when you can guarantee that all your queries or like interesting queries have equality operations in them. You do single key lookups, and they will limit your write overhead, and they will improve query performance where you can use only equality operations. Hash indexes are bad because they do not have index-only scans, they don't have ordering, no range operations, they cannot be a base for unique constraint, you cannot cluster a table over the hash index, and especially if you are using a PostgreSQL version below version 10, you are highly discouraged from using the hash index. Okay, so this is it from me, and Jobin, I welcome you to take over.
Thank you, Sergey. Great introduction about two indexes. So we are going to look at a Brin index now. Um, it's a block range index. It's an abbreviation for block range index. And here is a small illustration. If we have a series of blocks with continually incrementing values, it can be summarized as the minimum and max value of that range. Say in this case, the minimum value is 124 and the max value is 143. So this is the concept used in Brin index. So summarization of the entire range. This concept is in this index is introduced in Postgres 9.5, and it utilizes the concept of natural correlation of data with their physical location. So the data is stored in an incremental fashion or decremental fashion. So we can have a range of values. Uh, so the Brin index is not going to store the TIDs in its storage. Um, the underlying concept is to divide the table, split the table into a range of blocks, and the default range is 128 blocks. And the Brin maintains the summary data about the block ranges, basically the min and max values of that range. Um, and many times this comes into mind, the Brin is may not be a real index as such, because it is conceptualized as a improvement to the sequential scan to understand to which on which range of blocks the sequential scan need to be performed. So it can be thought of as a virtual partitioning mechanism of a table. So what range it need to be scanned, and the process of summarizing the data, the process of maintaining the Brin ranges is called summarization. Yeah, and now let's look at how it works in terms of the queries and statements. If we have a select statement, the bitmap index scan works by reading the each summary tuple. So we have ranges summarized as tuples, and the scan happens through the tuples, and comparing that with the query calls. Query calls means the what we specify in the work clause, and all the pages in that range are returned for the as a TID bitmap. Yeah, and this is from the query perspective. Now from the insertion, how the data is inserted. Uh, Maintaining this bitmap, the summarization will be an overhead to improve the performance, improve the insertion speed. The blocks at the end of the heap page may not be updated in the bin index in real time. So it's a work offloaded, and later the auto vacuum or vacuum scans uh, uh, does the job. The newly inserted blocks and generate corresponding bin indexes. And there is some improvement in from Postgres 10 onwards. We'll discuss that in coming slides. Okay, and the Brin index is burst to create a very small index because the entire block ranges are summarized. There is no TIDs, no are stored. So we have only the range information stored in the indexes, the min and max values in the range. I mean, um, and it is the faster in insertion. Yeah, and because the auto vacuum workers takes care of the index update later, and this is best used in time series data and sequential data. So nowadays we have a lot of IoT devices and which gives time series information, and Brin index is good for that. And where we should avoid Brin index. Brin index, since it stores the summary information about a range, we should avoid migrating the data from one block to another block. So to reduce raw migration, um, uh, make sure that there is proper fill factor. So reduce the fill factor and favor the hot update so that the TIDs will remain in the same block. Okay. And another common mistake generally we hear from customers is say they hesitate to use Brin index because the query performance may not be matching the B-tree index. Because the Brin index is not really a index as such. It's an accelerator for a sequential scan, giving the ranges of blocks it need to be scanned. So the query performance may not be matching the B-tree index where the real keys are stored and the TIDs are directly picked. But there are enormous other benefits. One of the biggest benefit is its size. As we can see in the screen, the first index is the default index, which is B-tree. We can see in a typical case, it is generating 114 MB. But if we switch to the Brin index, the index size reduces to kilobytes, 72 kilobyte, which is very small, very very small. So it helps in terms of cache and so the entire load on the system reduces. And the Brin index gives us ability to optimize how much blocks need to be summarized. So the uh, pages per range can be adjusted so that it can be more precise. So here is an example of altering an index to reduce the page per range. So default is 128. So now in this case, I am reducing that to two pages per range. So there is a slight increase in uh, size, but much better than the B-tree index. And once we alter the index, we should remember to re-index so that the entire things will be rebuilt. And we talked about the summarization effort by the vacuum and auto vacuum in the background. That happens automatically, but there is a way to do it manually as well. So if there is a bulk into inserts or there is a lot of things, this can be considered. But normally we won't recommend or do the manual way of summarization. Yeah, and coming to the improvement in Brin index in Postgres 10, uh, there is a concept called auto-summarization is introduced. Previously, regular auto vacuum used to take care of the summarization. Um, but what happens is there could be a lot of delays sometimes. Some use cases could lead to a lot of delays from the actual time of insertion and the summarization occurs. To avoid this delay, uh, from Postgres 10 onwards, Brin index requests a summarization run for the previous range as soon as the first tuple is inserted into the first page of the next range. So it is an explicit request to auto vacuum. Again, auto vacuum is in charge for processing this request, but it will be taken care as part of the uh, instead of waiting for a real auto vacuum to happen. Okay. The auto summarization is disabled by default, but can be enabled at the index level using auto summarization parameter. So here is an example. Now, this is one of the frequently asked question. So what are the columns which are best candidate for brain index? How to identify? So we can use PostgreSQL statistics at the table level. There are those columns which have higher correlation with its physical location are best candidates. Say in this example, I have two columns with correlation 1. It may not be 1 in many cases. It could be zero point 0.9 or 0.99. Yeah. So uh, any column which is having correlation close to 1 is good candidate for brain index. Okay. Now let's discuss about gin index. So GIN stands for Generalized Inverted Index. So the idea is the leaf nodes does not contain the column values. The keys are not stored in the leaf nodes. This is different from the B tree. The column values are the keys are stored in a entry key, entry tree. So I often conceptualize this as a hanging bat. So the entry tree is small from where all the leaf data nodes are referred. Um, so the data nodes are either a list or a tree of pointers to the actual rows. So we have there are two types of nodes here. We have the entry tree node where the actual keys are stored, and we have data nodes. The GIN postpones much of work by inserting new tuples into a temporary unsorted list of pending entries. So normally the data nodes are trees, but to maintain those data nodes, there is a effort. So it can potentially slow down the insert. So GIN has a provision to speed up insert by putting that entries into a pending list. Um, and this speeds up generally. And the gene index are much smaller than B-tree index because the key values are not, the keys are not stored in the leaf nodes. And here is the overall structure of gene index. As we can see, there is a entry tree where actual it's a almost a B tree structure similar to B tree, where actual values are stored, and from there the heap pointers are referenced in a posting tree. So from entry tree, the reference is to the posting trees. Here is another posting tree like that, and all the new entries will be kept in the pending list, and later the auto vacuum will be merging this to the actual posting tree. Yeah, and the gene index is very good for full text searches, and if and we know that there is some overhead in maintaining that, so it is good if there is less frequent updates, and best for less cardinality columns. So this is just opposite of what B-tree index is. And here is an example. The gene index is very good for text, full text searches, because as we can see in the screen, a lengthy text can be tokenized and converted into TS vector. So that only the very important keys which will serve the text searches will be identified. Now we have very small set of keys which need to be indexed. So what we can do is create a function index or expression index, which Sergey mentioned in the bitrate part. So store that those values as part of index. So this goes to the entry tree of the gene index. And we have two important parameters for gene index by which we can control the behavior of gene index and the efficiency. So one is the gene pending list limit, the size of the pending list, which need to be merged with the actual the gene index. This is used for speeding up. And as I mentioned, there is an option to speed up the pending list is used for speeding up the insertion. So we can turn it off and or turn it on. The default is on. That means the values will be going to the pending list. Yeah. And this is another beautiful concept. The gene index can be extended. So this an extension provided as part of the Postgres contrib modules. It's called bitrate gene. What is the need is when we try to create a gene index on a normal integer data type. It may not have the operator, and you may get an error like this. But we may need the gene index to take care of certain functionalities like bitmap index, which is available in other database systems like Oracle, where less locality values like say status code or sex markers, all those things um, can be Boolean values, etc., can be taken care. So gene index can be utilized as a replacement for a bitmap index. We just need to create this wrapper, B3 gene index, and then we can just use that for creating an index. And normally we can expect up to some 20 times space saving rather than just a normal uh, B3 index. And so this will be important for somebody who is migrating from other database systems. And coming to disadvantages of gene index, so gene index may not be a great idea if there are a lot of transaction, and occasionally there could be some delays because that's the time where the pending list is getting merged. Um, and most importantly, if somebody is deciding on gene index, make sure that it is properly studied and tested. That case. Um, and another overhead is since we have a pending list, the search need to be happening on the tree as well as the pending list entries. So this is additional work compared to other indexes. So there could be some slight overhead there. Mm, um, yeah, so normally the updates are fast, but if there are too much of updates are happening, so the pending list will grow, and there could be some delays because of that. And the another problem with the gene index is that the entry trees are not cleaned, even if there is some keys are removed, so it can become bloated. Um, yeah, and another problem is there are cases where more contention is reported in gene index than corresponding B tree indexes. Okay, coming to Bloom index. So the Bloom index works as a filter. Basically, it tells answers the question whether an element belongs to a set or not. The answer can be of two types. possibly in the set or definitely not in the set. Possibly in the set, in the set means it's a false. It can accommodate false positives, but the Bloom filter should give a definite answer for the negative test. So there should not be any false negatives. So that gives the Postgres the advantage of eliminating certain things from the query perspective. Yeah, and it works almost like a hash index, but it is we can think about as a more space efficient hash index. And the idea is there could be there are multiple hash functions at a time working on this on the value, the keys. Mm, yeah, and there is similarity with the hash index that only equality comparison works, equal to and conditions. And the efficiency of the index, the Bloom index, can be controlled using the signature length. The larger the signature length reduces the false positivity rate, but it can consume more space. So I usually picturize the Bloom index as a signature over a signature, because there are multiple hash functions working on the data. Okay, and we are going to see it can be even on multiple columns as well. So the Bloom index is very good for multi-column indexes where equality comparison is done. Um, yeah, and the advantage of Bloom index is the column position is not important. So in this case, we have a Bloom index created on a booking reference, booking date, and the total amount. But in my query, I have only filtering condition on the total amount, which is the last column of the index. But still, we can see that index is used. This won't be the case with the B-tree index. Yeah, and the efficiency of the Bloom index increases as we add more columns in the workflows. In this case, instead of specifying the total amount, I specified even booking reference. So the overall efficiency increases. So if you compare with the previous case, after the Bloom index lookup, it had to scan 772 blocks, but in this case, the index efficiency increased, and it has to look only for 3 blocks. And the signature length can be adjusted. That's a feature to improve the efficiency. And we can even specify the number of bits generated for each column. The default is 2. The higher the number of bits used, it will give more precision. So here is an example. The signature length is adjusted to 32, and number of bits used for column 1 is 2, second column is 2, and the third column is 4. So in this case, we have more precision for the third column. And one of the demerits of Bloom index is that we may not get all the operators for the Bloom index. And here is an example by which we can create our own custom operator classes. So in this case, normal hash function, which is used for hash indexing, is used for creating a Bloom index operator. By default, it comes with the integer and text operators, but we may have to create for other data types if we are planning to use for other columns. Yeah. And we should remember that the Bloom indexes are lossy in nature, but the normal hash index are more not lossy. The advantage of Bloom index is that it can work on multiple columns, but hash index are cannot do that. The Bloom limitation is a it's a as we mentioned, it is lossy in nature. It cannot be used in unique keys, and since it is lossy in nature, it will result in heap scan and recheck basically, and it cannot use for null searches, null value searches. And gist index. GIST stands for generalized search tree. The structure is similar to B tree. Why we need a GIST index is that we have support for a lot more data types like geodata, images, and normal operations like equal to comparison or less than or greater than. All this may not be working for this uh, type of data types. So we may have to define our arbitrary data types and operators on the top of that. So GIST provides an extensible framework for building new access methods, and GIST is very good for overlapping data types. So that's the reason why we use it for text searches as well as geospatial data. Yeah. And when it comes to the text searches, the GIST index uses a compact solution called signature tree. And disadvantage is the efficiency may degrade over time. Yeah, if there is a lot of data changes, the periodic reindex may be required. And here is an example of using R tree, just R tree. As we can see in the screen, the rectangle, the blue line, the bigger ones, say the R1 and R2, are the big boxes, and there can be it can be divided into smaller boxes. Mm. So the index stores the rectangle where the point lies within. So the root of the tree is the biggest rectangle, and the leaf nodes are points. The points means it is the rectangle of zero size, so, zero area. And searches like as shown in the screen, like whether a point belongs to a box can be satisfied by this index, and we can even use it for ordering, say order by points as in terms of distance from another point. So these are special operators which can be supported by GIST index. And here is some examples of point data type. Some of the sample operators of point data type. So whether a point is strictly on the left or right, or is it coincides, etc., and whether it is contained in a rectangle, in a polygon or circle. So these are the additional operators, examples of additional operators just can support. And since the GIN and the GIST index are used for text searches, it is a very frequent question, which is the best. So this is a comparison. The GIN index is very good for fast lookups, but GIST is comparatively slower in lookup. But GIN is slow in updates. GIST is faster in updates, and GIN actually stores the real lexemes of the text search, but GIST is storing only the signature. And GIN can be speeded up. The index maintenance can be speeded up using maintenance workmem, but the maintenance workmem don't have any effect on GIST index. These are the major difference which we should be keeping in mind while selecting the index type. And here is an example of some of an improvement came in Postgres 13. The GIST index signature length can be modified. because Postgres 13 allows passing these kind of parameters to indexes, index specification. And the same information will be displayed in when we describe the table. And quick overview of SP, GIST, and RAM index. So the just like GIST index, the SP GIST also is a kind of framework for creating a lot more types of indexes, but it is a non-balanced tree. The concept is repeatedly divide the search space into partitions that need not be of equal size. So it need not be overlapping. It shouldn't be overlapping. Yeah, SVGIST is suitable for structures where the space can be recursively split into non-intersecting areas. So some of the specific types of indexes which can be derived out of this is uh, mentioned here. And as we can see in the diagram, it is a quad tree. The space is divided into boxes, so until it reaches to the minimal point. Yeah, it's a remember that is a non-balanced tree. And the rum index, this is an example for external index. Postgres supports creating custom indexes as extension. So this is created as extension. um, the underlying concept is based on the gene access methods, and the problem which the rum index is trying to solve is that it is even capable of storing the positions of the text lexemes. Say when we use the text search text indexing in gene index, it stores the keys and but it is not storing the position. But the position is important for a phrase search. The phrase need to have the proper order of the wording, right? So in those cases, RAM index is useful. And there are disadvantages also. It is slower to build. Insert time is slightly higher than gene index. And another disadvantage is it uses the generic val records. The val records are not so efficient as the other index. So a lot more information will be there in the val. Yeah, here are some additional information, additional references. And thank you all.
Thank you, Jobin. Thank you, everyone.